Hello all, I am Dr. Sukhpreet Kaur and I am going to today introduce with you the theory of automata and one different type of automata, which is the finite automata. So let's start with the theory of computation. In theoretical computer science and mathematics, the theory of computation, it is the branch which deals with how efficiently problems can be solved on a model of automation using an algorithm, and this field is further divided into three possible branches. First one is the automata theory, which we are going to discuss now, and a computability theory and the computational complexity theory. Now, what is an automata? Automata is the plural of the automata, and it simply means any machine. Like we work on a computer, so it is a machine. Automata theory, it is a study of the abstract machines and the problems they are able to solve. Automata theory, it is related to the formal languages theory, as the automata are often classified by the class of formal languages they are able to recognize. So automata is basically used for the evaluation of formal languages which the computer can understand. There are two types of languages, informal languages and the formal languages. Informal languages like we speak, English, Hindi, Punjabi, these are all informal languages that if we do not use the proper grammar, the proper words, the other person can understand, but the computer can only understand the formal languages. So basically automata theory, it relates to the formal languages which computer can understand. So why we need to study automata? It is used in a variety of properties concerning the models, grammars and the languages which will be proven, and here I am referring only about the computer languages. These algorithms, they form the basis of the tools for processing languages, for example, parsers, compilers, and the assemblers. These all are the system programs which are used for the automata, and other algorithms will form the basis of the tools that automatically construct language processes, for example, YARC and LEX. LEX and YARC, they are the automatic lexical analyzer as well as the syntax analyzer. So all the system programs, if we want to run the system programs, we need to learn the automata. Only with the help of the automata, basically, which I am going to discuss with you, finite automata, that are the basis of LEX, YARC, compiler, assemblers, all type of translators as well as the system programs. So, types of automata. According to the Chomsky, this is the scientist who gave the classification of the languages as well as the automata. Languages are the formal languages, and for all the different type of four languages, we have four types of automata. These are the four automatas. First one, we have the finite automata, push-down automata, linear bounded automata, and the Turing machine. So I am going to start with the finite automata first. Finite automata, informally, a state diagram that comprehensively captures all possible states and the transitions that a machine can take while responding to a stream or a sequence of input symbols. It is a formal system, and it is a recognizer for regular languages. As you already know about the four different type of languages. So formal languages are fourth-time languages, and the regular languages can be evaluated or can be accessed with the help of the finite automata only. It remembers only a finite set of states, that is why its name is finite automata. And any problem can be presented in a form of decidable problem that can be answered as yes or no, right? So there are finite automata in which we have the outputs in the form of yes or no, or we can have the output in the binary form or in the decimal form, anything. That is a finite automata with outputs, right? So why should we study the finite automata? Again, the same which we have studied for the automata. It is used for both design and verification of the circuits and the communication protocols. It is the biggest application of the finite automata. And it is used for many text processing applications, and it is an important component of compilers. It also describes simple patterns of events. Once you will be clear about the finite automata, that how the state diagram of the finite automata is made, you will be very much clear how it can be used in all of these applications. Next, we have two different types of finite automata. First one, we have the deterministic finite automata, and second one, we have the non-deterministic finite automata. Now, let's start with the deterministic finite automata. Three words in the deterministic finite automata, DFA. First one is a deterministic. What do you mean by the deterministic? Deterministic is a that machine will be in a sum state. Upon receiving of a certain symbol, it will go to a known unique state. Means we know the next state which will be there. Next, second term, we have the finite. As I have already told in the definition of finite automata, that finite means the machines only have a certain number of states. And automata, which I have already told you, that automata means a machine. Now, the formal definition of DFA. A DFA consists of 5 tuples. These are the 5 tuples. First one, we have capital Q, which gives you a finite set of states. Then we have the sigma, which give you a finite set of input symbols. Then we have a start state that is represented by a Q naught. Then we have the capital F, which is a set of final states. And last we have the delta, which give a transition function, which is a mapping between the combination of the present state as well as the present symbol. The combination of the present state and the present input symbol will give you the next state. This is the transition function. So a DFA is defined by the 5 tuples, that is capital Q, sigma, Q naught, capital F and delta. So this is the block diagram. It's very interesting to learn how the DFA works, right? This is the block diagram. The various components of the FA are the input tape, right? We have the tape reader, that is the read-write head, and we have the finite control. So what is basically done over here, we will start with the first symbol. Like you can see in the input tape, we have the combinations of zeros and ones. That is the input that we will give to our system to whether it can recognize this language or not, right? Like it will start from the first symbol. It will check the state. As I have already told you that with the transition function, it will check out the combination of the present state and the combination of the present input symbol. It will give you the next state, right? It will traverse all the things. Starting from the first 0, it will move to this last 0, right? One by one, it will transit to all the symbols and it will find out the final state. If at the end it will reach the final state, means your string is accepted or the language is recognized by this finite automata. I will give you this in detail now. Now, at regular intervals, the automata reads one symbol from the input tape and then enters into a new state. That depends only on the current state and the symbol just read, right? So here we can see, you can see the first symbol, like in this, suppose the read-write head is at 0. So it will take the present symbol under the read-write head, that is 0, and it will take the state which is in the finite control. The combination of these two will give you the next state plus the movement of the read-write head towards the next symbol. Means after this 0, the next symbol which will be accessed by the automata will be 1, right? Now, after reading an input symbol, reading head moves 1 square to the right, as I have already told, on input tape, so that on next move, it will read the symbol in next tape square. The process is repeated again and again. Like in this case, you can see, it will start from this 0 and it will move until we have the terminator at the end or the last symbol. Like in this case, we have the 0. It will process all the symbols and at the end it will check the state of the finite control. If the state of the finite control is one of the final state, means this string is accepted by this automata, right? So last, if it winds up in one of the final states, the input string is considered to be accepted. The language accepted by the machine is the set of strings it accepts, right? So next we have the representation of finite automata. There are 2 representation techniques of finite automata. First one, we have the transition diagram, and second one, we have the transition table, right? Transition diagram, it is the graphical representation of finite automata, and transition table, it is the tabular representation of the finite automata. So first of all, I am going to discuss about the transition diagram. A transition diagram is a directed graph. It is a directed graph where nodes represent states, right? That we have all the states in the capital Q in the finite automata, and the states, they are connected with each other using the directed edges. It is the directed graph, means all the arrow, they have a direction. The edges are labeled using the input characters, that is the elements of sigma, and the initial state of the transition diagram is represented by this, means a state, all the states, they are represented by a circle. But if an arrow is pointing, an empty arrow is pointing to any state, it will be an initial state. The final state of the transition diagram is represented by the two concentric circles, and the transition of the finite automata is represented by this. You can see from here, right? It is the start, means it is the initial state. On getting a symbol 0, it will move to the state Q1, right? This is the transition. So this is about all the components of finite automata. We have the 5 tuples of finite automata. First one, we have the Q, the set of states, and all the states, they are represented with a circle. Second, we have the sigma. Sigma is for the input characters, which is the labeling of the edges. Then we have third symbol, initial state, which is represented by a empty arrow pointing to a state. Then we have the final state, which is represented by 2 concentric circles. And last, we have the transition function, which is shown over here like this, that on getting 0, when your automata is at a Q0 state, it will move to the next state, that is Q1. So I will show you the transition diagram for this. You can see from here, let us draw a transition diagram for a DFA. First of all, I will want to define about the DFA. These are the components of DFA. First of all, we have the states. There are 3 states, Q0, Q1 and Q2. You can see from here. Sigma is 0, 1, means it can take any input character from 0 and 1 only. And these are all the transition functions. How we write the transition functions? Delta is the symbol of the transition function. The present state is Q0. If at a Q0 state, it has a symbol 0, it will move to the Q1 state, right? For this, we will make the transition in the transition diagram like this. As we know, initial state is Q0, we will make the start and Q0. On the Q0 0, it will move to Q1. You can see here the edge over here, that we have the edge Q0 connecting to the Q1. It is a directed edge with the label 0. That when at a 0 Q0 space, it will get a 0, it will move to the Q1 state. Now next we have the Q0 1, it will give you the Q0 only. We have a self loop, right? At a Q0 state, if it will get a 1, it will remain at the Q0 state. It is a self loop, right? Next we have the transition from Q1 upon a symbol 0. When at the Q1 it has a symbol 0, it is a self loop, right? Next we have Q1 1, it will move to Q2. As Q2 is the final state also, so we can give this with the concentric circles. Next, at the Q0 state, if it gets a symbol 0, it will remain at Q0. We can see a self loop. At a Q0, if it gets a symbol 1, it will remain at the Q2 state, right? So this is how we define the DFA. This is how it can be represented with the help of a transition diagram, right? 5 tuples, again I am repeating, 5 tuples, Q, sigma, delta, Q0 and the final state, that is Q2. Now, how we check the acceptance of any string with the help of transition diagram? Any string, it is accepted by the transition diagram if there exists a path from the initial state to the final state, right? And concatenation of the labels of the edges traversed is equal to the string to be checked, right? Now let us check for 0, 111. Let's start, always we will start from the start symbol. We have started from here. The first symbol we need to process is 0. At a Q0 state, if we get a 0, we will move to which? Q1 state, right? Next we have the symbol 1. Now at the Q1 state, if we get the symbol 1, we will move to the Q2 state. Next we have 1. If at 1, we will remain at the Q2. Last symbol is again 1, we will remain at a Q2. Means after the processing of all this string 0, 111, we reach to the final state, that is Q2. So this string is accepted by this transition diagram, right? Second, let's check it for another string, that is 00. Now starting from again from the initial state, if we have the 0 at the Q0 state, we get the 0, we will reach to Q1, right? And again the second symbol is 0. While processing the Q0 0 symbol, it will remain at Q1 state. String is finished, but the state is Q1, but Q1 is not the final state. So this string is not accepted by this transition diagram, right? I think it's very much clear from here how we can draw a transition diagram and how the strings are accepted by the transition diagram. Let's come to the another. So let's start with the transition table, which is another representation technique of the DFA. So we will again draw the transition table for the same which we have drawn the transition diagram. Here you can say it is the form of a matrix, right? In the rows section we will write all the states, which are the states of the finite automata. There are 3 states, Q0, Q1 and Q2. Here we will write all the states, and 0, 1, these are the input symbols. These will be at the column, right? 0, 1. Now how we can do the transition, how we can write the transitions? You can see from here, delta Q0 0 means you are at the state Q0, and when you will get a symbol 0, you will move to the Q1 state. So at the intersection of Q0 and 0, we will write Q1, right? Similarly, for the delta Q0 comma 1 means we are at the Q0 state and we have the symbol 1, we will move to the Q0 state. You can say at the intersection of Q0 and 1, we will write Q0. Similarly, we have delta Q1 0, it is Q1, delta Q0 1, it's Q2, delta Q2 0 is Q2, and delta Q2 1 is Q2. This is how you will draw the transition function. Then we have the initial state. You can see an arrow, it refers to the initial state, and the final state, a star. Either you can write a star or you can circle it with the concentric circles. It will show you the final state. Any way you can find out. So this is how we can represent a transition table, the finite automata. So acceptance of the strings, this is the algorithm which I have already defined you in the transition diagram. So this is in the algorithmic form, how we can accept any particular string with the help of the finite automata. First of all, we have the input, means we need a string that we want to be accepted by this finite automata. Then we have the question, whether this string is acceptable by the DFA or not. How we can do steps? First of all, as I have already told you, that we will start from the start state, means the initial state. For every input symbol in the sequence, means you can have a string of length 5, you can have a string of length 6, 7, 10, any length. You will start from the first letter. For every input symbol in the sequence, you will compute the next state from the current state, given the current input symbol and the transition function, right? With the help of a transition function, you will find out the next state. How we can find out the next state? With the combination of the present state and the present input symbol. If after all symbols in W are consumed, means you have traversed all the symbols, and at the end you reach to some final state. Means your string is accepted by this particular DFA, otherwise it is rejected by this W, right? So now we have completed with the deterministic finite automata. Deterministic means we have a unique next state after the combination of the present state and the present input symbol. But now I am going to start with another type of finite automata, that is non-deterministic finite automata. A non-deterministic finite automata is of course non-deterministic. It implying that the machine can exist in more than one state at the same time. More than one state means now we do not have a unique state. It can reach to number of other states on the combination of the present state and the present input symbol, right? Transitions could be non-deterministic, like in this case, at this state, QI state, upon taking a symbol 1, it can either move to this state or it can move to this state. It can be number of states. Here I have shown you 2 states, but it can move to a number of states. Each transition function therefore maps to a set of states in the case of non-deterministic finite automata, but in the case of DFA, it has to be in a single state, right? So definition of NDFA, now we will see, we have already done with the formal definition of DFA. Now we will see what is the definition of NDFA and how it is different from DFA. Now come, a non-deterministic finite automata, it consists of these 5 tuples. The tuples are same, you can see from here, Q, sigma, Q0, F and delta. Now what is the difference? Q is same, it is a finite set of states. Sigma, it is a finite set of input symbols. Q0, it is a start state or the initial state. F is a set of final states. Here we have the difference over delta only, right? It is a transition function which is a mapping between the input symbol and the present state, it will give you a subset of Q. In the DFA, we will have only a single Q, but here we have a subset of Q. You can say it is, NDFA is also defined by the 5 tuples, but the difference between them is only in the transition function only, right? So now next, take an example. This is an example. Here you can see from here, I will tell you over here, the set of states, you can say 3 states, Q0, Q1 and Q2. Del sigma is 0, 1, start state is Q0, final state is Q2. Here you can see the difference in the transition table. In the case of DFA, we were having a single state at every intersection of a state and a symbol. But in the case of NDFA, we have a subset of states. You can see from here that if it get a Q0 at 0, it can go to 2 states, either Q0 or Q1. You can see from here also, start, agar if it gets a Q0, right? From the Q0, if it gets a symbol 0, it can remain at Q0 or it can move to Q1. So here the non-determinism is here, right? Another thing over here is that in the case of NDFA, we can have empty transactions also. Means like in this you can say that on, if it is at a state Q1 and it will receive a symbol 0, here you have a file, means no transition is defined. But in the case of NDFA, these empty transitions can be there, but in the case of DFA, empty transitions are not allowed. We need to have a state, or we need to use a dead state combination, so that every symbol and every state should be defined, right? So we have done with how we need to use a DFA. Now we have to know how we used to do an NDFA, means how we can do a processing of any string with the help of an NDFA, right? Same, we have the input symbol which we need to process with the help of the NDFA. Question, we have to find out whether this string is acceptable by the NDFA or not. Again, we will start from the initial state, which is the process of FA, that we have to start with the initial state. We have to start with the initial state, right? Then for every input symbol in the sequence, we will determine all the possible next states. See the difference? In the DFA, we will always have a one combination, but in the case of NDFA, we need to determine all the possible next states from the current states given the current input symbol in W and the transition function, right? If after all symbols are consumed, we have traversed all the input symbols and at least one of the current state is a final state. As we can reach to a number of states on consuming a single symbol, so at the end we need to check out all the states which have reached, right? So if we have reached to at least one of the final state, means the string is accepted, we will follow that path only, right? If the string is not accepted, we didn't reach to any final state, means the string is rejected by this automata. Next, we need, which is very important, that what is the difference between deterministic finite automata and the non-deterministic finite automata, as we have made it clear that what is deterministic automata and what is non-deterministic automata, the difference very should be clear. In the case of DFA, all the transitions are deterministic, means each transition, it leads to exactly one state, right? In the case of NDFA, some transitions can be non-deterministic, means we can reach a number of states, we reach to a subset of states. Second, for each state, transition on all the possible symbols should be defined. As I have already told you that each and every symbol transition should be there in the case of DFA, but in the case of NDFA, the empty transitions are also allowed. Not all symbol transition need to be defined explicitly. We can have an empty, that is the phi transitions also. It will accept the input if the last state is in final state, right? It will accept an input if one of the last state is in F, right? In the DFA, we will reach to the single state because it is a deterministic, but in the case of NDFA, we will reach to the number of states, right? So, final state should be a final state. Sometimes harder to construct because of the number of states, as we need to find out the unique states. So it is harder to construct DFA, but it is easier to construct a NDFA, right? Although power of NDFA and DFA is equal, right? If you will process any string with the help of a DFA as well as with the NDFA, the power is equal. The strings can be easily accepted by DFA as well as the NDFA, but while you are constructing, the DFA is little bit difficult to construct instead of NDFA. So the process of constructing a finite automata is basically you start the construction with the NDFA only, then you convert that NDFA into a DFA. That is much easier process, right? Practical implementation is feasible, but the practical implementation has to be deterministic, means NDFA cannot exist alone. We need to convert that NDFA every time to a DFA so that it can process the regular languages. So I think after this it was pretty much clear that what is the DFA, what is the NDFA, and what is the difference between the both, right? So how we need to develop a DFA? DFA, this is, I'm going to tell you a number of examples how we can develop a DFA, right? For that, what you need to do, suppose we need to build a DFA for any binary string, we need to find out what is the input symbols, means how many different symbols we will be interacting with. Like we have this W is a binary string that contains 0, 1 as a substring, right? So we need to find out which is the input symbols. Here it's clear that 0 and 1 will be the input symbol. We need to decide on the states, we need to find out the transitions, how the transitions will be there, and how the final state will be there, how it will reach to the final state, and we have to find out other states also. We will take a little bit of examples, you will be very much clear how we can do that. Before that, I will start with a small video that which we have discussed till now, right? What is that or DFA, NDFA, and what is the difference? It has been created by the Powtoon. Let's start with this. So, like you can see from here, this is the finite automata, which I have told you all the different tuples of the finite automata, right? It can be represented by the transition diagram. You can see from here, right? Simplest examples for the transition diagrams. You can see, then this is the transition table, which I have told you that these are the input symbols, right? These are the states. Initial state is represented by this and final state by this. Then we have discussed about the deterministic finite automata. This is the deterministic finite automata, means on a unique symbol you have a single destination, right? Now second one is the non-deterministic, means on a combination of the present state and the present symbol you reach to number of states. Here you can see this is a self loop. Either you can remain at Q0 and you can move further. Then you have the ENFA. This is epsilon NFA, means on the empty state without consuming a symbol you can move to the other state, right? Let's start with the developing of finite automata, right? So first of all, a simplest example of finite automata for the language that contains 0, 1 as substring, right? We need 0, 1. So first of all, we need to find out what is our sigma, right? Sigma is the input character. We have two symbols, that is 0 and 1, right? So which is the substring, means the minimum symbol which will be processed by this finite automata will be 0, 1, right? So first of all, we need to find out, in many cases we need to find out the minimum string that will be processed by the finite automata. Like in this case the minimum string is 0, 1. So how we'll draw the automata for this? This will be your initial state, as it is given by an arrow, initial state, right? The first symbol to be processed is 0. The first symbol to be processed is 0, right? Then we will reach to one state, that is Q1, and the second, we need the second symbol is 1. This is 1, and now this will be your final state, that is Q2. This is the simplest part, that first of all find out the minimum string that will be processed by this automata, right? Then you make this to the combination of the directed edges. Now another thing, as we are drawing this DFA, we need to find out that there can be strings also of this type, right? In that 0, 1 is again a substring. So what will happen if we get a 0 or 1 over here, right? Here we know that at a Q0, upon getting a 0 it will move to Q1, but if it get a 1 over Q0, what it will do? Say it will be a self loop, because we need not to increase the number of states. That is why the construction of DFA is it's little bit difficult. We need to find out the number of states, right? So upon getting a 1, it will remain at Q0, and upon getting a 0, it will move to the next state, right? Again, when it is at Q1, it will get 1, it will reach to the final state, because the final thing, that is substring condition, will be fulfilled. But in the case of this 0, it will remain over here, right? Upon getting a 1, it will reach to the final state Q2. Now this, which was the condition, that 0, 1 is a substring, 0, 1 is a substring, right? So the condition is fulfilled, that 0, 1 substring is there, you reach the final state. Now that can be string also of this form, that we have a 0, 1, 0, or we have a 0, 1, 1. In this case, substring is fulfilled, but after that we have a number of symbols also. In that case, we are at the final state. We can get 0 or we get a 1, right? It doesn't matter, it will remain to the final state because the condition is fulfilled. This is how you will draw a finite automata. But in the case of DFA, you need to clear that upon every symbol you want to have a transition. So if you want to draw a table for this transition table, as I have already told you, that at the row column you will write all the states. You can write over this. This is the initial state, this is Q1, and this is Q2. Here you have all the states, right? Here we will have all the symbol. We have the symbols 0 and 1, right? Upon Q0, if it had a 0, it will move to the Q1 state. We will write the Q1 over here. Upon getting a 1, it will remain at Q0 state. We will write the Q0 over here, right? Upon getting a 0, it will remain at the Q1, right? Upon getting a 1, it will move to Q2, right? Upon getting 0 or 1, it will remain to Q2, right? This is how you will draw, right? So another case, suppose you want to check out the processing of the string 011 from this transition diagram. How you will do? You will start with the initial state. Initial state is Q0, and the string you need to process is 011. First of all, you will find out the combination of this present state and the present input symbol, that is Q0 0. It will move to Q1. You will write that Q1 and the string remaining will be 11, right? Then you will find for Q1 1, Q1 1, it is Q2. You will reach to Q2 and the symbol remaining will be 1. Now you will find about Q2 1. This is Q2 1. It will reach to Q2, right? And the string will be empty. Means when your whole string is processed, you reach to a final state, means your string is accepted. Now let's take a case. Suppose I have the case of, say, 00. The string which does not have this substring, that is 01, right? So what we will do, upon getting the first 0, Q0 0, it will be at Q1 state. Upon getting another 0, it will be at the Q1 state. Now your string is processed, all 00, but the reach state is Q1, but that is not the final state. So 00 will not be accepted by this transition diagram, by this DFA which we have constructed. So after building of the DFA, you need to find out, you have to check for one of the acceptance or one of the rejected strings, so that it should be clear that you have constructed a clear DFA. Either you can draw a transition diagram or you can draw a transition table, anyone will work, and you need to check out whether the strings are accepted by this or not. Now let's take another example for this. Now I have the finite automata for the language over 0 and 1 that end in 1, right? Now again, first of all, we will find out what is our delta is. Delta is input character is 0 and 1. The condition is that end in 1. The string can start with 0, but it will always end with a 1, right? So here we will have an initial state, right? The strings that end with 1, it can be a single one, it can be a double one, it can be a 0 1, it can be a 001, it can be a 1 0 0 1, right? Anything. So we need to take care about each and every string which can be the part of this automata, right? So the automata which we will draw, it will accommodate all the different strings that end with 1 and have the input symbols either from a 0 or from a 1. So how we will do? Like in this case, we know the minimum symbol is 1. So upon getting a 1 from the initial state, it will reach to a final state, right? This is how it will process 1. Now suppose we need to check out if our string starts with a 0. If our string starts with a 0, if our string will start with a 0, it will remain at the initial state, because only after getting a 1, it will be at the final state. Now when it reached to 1, let's see with the case 1 1, right? Upon getting the first one, it reached to the final state. Our condition is fulfilled, right? So when the second one will be there, what will happen? It will remain at the final state. This is about this one also. Now this is pretty much done. 0 1, 001 can also be done, 001, right? Now suppose it has this case 1001. Condition is fulfilled, that ends with 1. So upon getting the first one, it will reach to the final state, right? On getting 2 zeros, where it will go? It will remain to the final state only. It will remain to the final state. Can it happen? No, because in this case 1001, what you will do? It will also process the thing 100. So instead you will have this one. Clear? Because we need to check out that the last string is 1. Last string is 1. So you will backtrack from the Q1, from this final state to the Q0 if it gets a 0, right? If it gets a 0. So in this case we have made a DFA. We have made a DFA with which we can recognize all the language which ends with 1. So if you need to draw a transition diagram for this, here you will have a 0, here you will have a 1, here we will have a Q0, right? Here we will have a 1. So this is our final state, this is our initial state, right? Upon getting a 0, it will be at Q0. Upon getting a 1, it will be at a final state. Upon getting a 0, it will backtrack to Q0. At a 1, it will be remain over here. So this is a finite language over the 0 and 1 regular language that end in a 1, right? So this is another example. Let's come with the second one, that is FA for the language having odd number of ones, right? Odd number of ones means we can have a 1 1, then 3, then 5 and so on, right? So the concept between this type of automata is that what we will do, that on getting a even number of ones, two conditions, either it can have even number of ones or it can have an odd number of ones. If it get an even number of ones, it will end up on a non-final state. It will end up at a non-final state. But if have a odd number of ones, it will reach to a final state. This is the basic concept. If you need to find out for the even number of ones, the question can also be there that you need to find out for the even number of ones. For the even number of ones, you will do the different case, that for an even number of cases it will reach to the final state. For the odd number of cases, it will end up at a non-final state. So let's see how we can do with the final state. As the minimum string is what? 1. So you will start with the Q0, right? Minimum string is 1. Upon getting a 1, it will reach to the final state, that is Q1, right? So second is what? After getting a 1, it can again get a 1 over here. So what we will do? Upon getting a 1, it will reach to the non-final state, that is Q0. Again it will get a 1, odd number, it will reach to the final state. Let's see what will happen if we need to process a string with 5 ones with this type of automata. What it will do? Let's see. We will deal with the help of this Q0 and 5 times 1, right? What it will do? Upon getting a first one, it will reach to the Q1 state. Number of ones left will be 4. Next, upon processing the next one, it will reach to the Q0 state, right? And the number of ones will be 3. Next we have again Q0 and 1, it will reach to Q1 state and number will be 2 now, right? Then we have Q0 and number will be 1. At last we have Q1 state when your string is empty. This is our process, right? Once we have completed, we have traversed all the string, the state we have reached is Q1. It is a final state, means your string is accepted by the automata, right? So as I have already told you, this is for the odd number of ones. We can change it with the even number of ones also. If you need to find out for the even number of ones, what you will do, because in the case of even numbers you will have 2, 4 and an empty string also, because 0 is the even number also. So in that case, if you need to process an empty string with this, your initial state will be the final state also. Your initial state will be your final state also. In that case, what you will do, upon getting a 1, first one, it will move to the non-final state, right? Upon getting another one, it will move to the final state. So this is for even number of ones, this one. This is for odd number of ones. So I think it's pretty much clear how you need to develop a finite automata for the even number or for the odd number or for any string, right? I am again repeating the same concept. If you need to find out, develop a DFA, right, for any language, first of all, in a many numbers, you need to find out the minimum string. You need to find out the minimum string. If you get the minimum string which is to be processed by this finite automata, what you will do, you will make a path of that minimum string starting from the initial state to the final state, right? Like in this case, our minimum string, in the case of odd number of ones, our minimum state was 1. So we have made a path from the initial state to the final state with the label 1, right? So in the case of even number of ones, the minimum number was empty, that is 0. So in that case, we will have made the initial state same as that of final state. If your initial state is same as that of final state, means the length of the string that is to be processed by this automata is null, is empty. So this is the finite automata for the language having odd number of. So now we will discuss about how the finite automata can be used for the processing of words, any words, right? Her, he, she, like I have taken the example of 3 words, her, he and she. How we will do, we will start with the initial state, right? Here you will check out the first symbol of all the strings, H, H and S, right? As we are drawing a finite automata, so we will have a symbol H and a S, 2 strings from the initial state. If it will get a her or he, your state machine will go to H, this path. If it get a S, it will go to this path. Next we will reach to some state, say Q1 in this case and Q2 in this case, right? Next symbol we have E. Next symbol we have E. So upon getting an E, it will move to the next state, Q2. Now see over here, he it need to be accepted by this input string, so we need to make it a final state, and we will write here return he, or you can say except he, any word you can write just to find out that he is being accepted by this state machine. Next, if it get a R over here, right, it will move to the new state Q3, right, and here it will be return her, right, or in many cases you can see a loop over here, with the name R, right, and it will be return her. Any cases, for that case then you have to delete this, you will write this, right, anything. Then we have H, we are processing she, right, so here we will have Q3, and last we have the E, so this will be the final state, right, so here we will have return she, right. So why I am telling you, because this is the biggest application of your finite automata in the case of compilers. So you write a program in your C++ window, in your Java window, anything, right, then you compile that program. How your system compile that program? It will first find out the keywords. You know the processing of the compiler. First of all, it will check one word one by one. So in the case of lexical analysis, right, what it will do, it will start from the initial state, check each and every symbol. If it matches a keyword, it will give an output that it's a keyword. If it matches a relational operator, it will that it is an operator, right. If it matches to any variable, it will it is a variable. If it matches to any integer, the output will be integer. So we have the state machine, we have the state diagrams, we have the finite diagrams for each and every symbol that will be recognized by the compiler in the form of lex, that is a lexical analyzer, in the form of a yak, that is yet another compiler. Automatic syntax analyzers are working in this way, right. So after this work, it will tell you that whether it's a keyword, whether it's a symbol, you need to make an entry in a symbol table. This is basically for the recognition by the compilers, right. So next we have DFA for recognizing words that start with the same alphabet. Like we have the two words any and. You can see any and, right. Common word is what? This. Once you are drawing a DFA, as you know that how the DFA is designed, like in this case, right. So we have the first symbol A, which is same. So in the case of DFA, when we have a unique output, so we will have a single symbol A and we will have a single output. Second is also same, so we will have a single output. Now the third one is different, Y or D. So we will have two outputs from here. Upon getting a Y, it will reach to the final state Q3 and it will give you that it's a return N, right. So upon getting a D, we will reach to the final state Q4, right, and it is return and. This is how you will do a DFA. You will do a DFA upon a intersection of a unique state and a unique input symbol. It will give you a single state. But if you need to draw a NDFA for this, the same thing, you need to draw the NDFA for this. How will you do? Right? You will have A, you will have A, right? Q1, Q2, same N, Q3, Q4, this is for Y, Q5 final state, this is for D Q6 final state, right? So this will be return any, right? Or you can use the term except, right? Here you will have return or except and, right? As we are drawing NDFA, non-determinism is there. For the same symbol you have the two states for the same symbol. From here you will come to know that whether, agar suppose in this case you need to process any, but you have chosen this path. After reaching here you will find out that there is no transition from the Q4 on the input symbol Y, so you will backtrack. You will do the backtracking, but that is the difference between the DFA and the NDFA, right? In the NDFA you need to backtracking because you have a subset of paths. You can choose a number of paths. So if you get a failure at any path, you need to backtrack, you need to check out where the alternate paths are there so that you can process your strings. You need to check out all the different paths. But in the case of deterministic finite automata, you have a single path, right? You will find out whether there is a path from this on this particular symbol or not, and you can easily find out whether your string is accepted or rejected. But in the case of NDFA, as you have the same path for the same symbols, right? So you need to backtrack again and again so that you reach to find out a particular symbol, right? So this is about the NDFA and DFA. So I am concluding this again to you that we have two types of finite automata. First one we have the DFA and second one we have the NDFA. DFA is deterministic finite automata and NDFA is non-deterministic finite automata. So what is deterministic finite automata? Deterministic finite automata is basically when we have the determinism, means on a combination of a present symbol and the present input state symbol, we need to a unique state. We need to go to a unique state, means transition of a state and a input symbol will give you a single state. This is what DFA, right? But in the case of NDFA, we have the non-determinism. Non-determinism in this case is what? On the combination of the present state and the present input symbol, we reach to the number of states. We reach to the number of states. So this is the non-determinism. Although, as I have already told you that the power of DFA and NDFA is equal. This is not the case. If any string is processed by a DFA, it will be processed by NDFA for sure, right? But the construction of DFA is bit difficult and the construction of NDFA is bit easy. The reason is that we need to find out the finite number of states, but in the case of NDFA we can do a empty states also, and we have no restriction that all symbols should have a unique state, right? We can reach a number of states. So in this case, while in the case of NDFA, what we can do, we can draw. First of all, we can draw a NDFA for any particular language. Suppose you have a regular language, you will draw the NDFA for that, and from that NDFA you will draw a DFA. This is much easier process. So instead of developing a DFA for the difficult processing, difficult regular languages, first of all you draw the NDFA, and from that NDFA you must draw a DFA, right? So this is the process of the development of the finite automata. So this is all about the today's lecture of finite automata, in which we have discussed the finite automata, its basics, how the block diagram, how we have done the processing of the DFA and the NDFA both, and how we can develop a DFA, right? So I think it's pretty much clear, and thank you for